Hello, for chapter 5, we're going to be covering energy. The biggest way that this is going to apply for food science is going to be cooking, but we're just going to cover energy kind of in general terms. We'll infuse a few food science examples as we go for this section, and then probably more next week we'll be talking more about how it relates to food science. But there are some examples in this section too. So for this section of chapter 5, it's going to be from page 117, the beginning of the chapter, until 129. So it's a little bit more than half of the chapter that I'm covering in this lecture today, mostly because just where I'm ending is a good stopping point for the section. So, okay, what is energy and why are we studying it? So energy is very simply defined as the ability to do work. And the reason why we're studying it is that it's often manifested as heat. The study of heat transfer can be really important for food science, especially when we're looking at the way heat transfer affects food products. So, for example, pasta. So the transfer of heat and water, and at what point is pasta overcooked versus done well? Not well done, but done well. Um, so, like, for example, if you've ever eaten Chef Boyardee pasta, that is a totally different texture than al dente nice spaghetti that you make at home, right? And a lot of that is because of the limitations of canning, because things are going to be overheated and pasta is going to be overcooked when you can it. I feel the same way also like frozen pasta. Most frozen pasta is real bleh to me because it's overcooked. Um, how well done steak is another example. Um, so there is a difference in not only what it looks like, but as you should noticed if you were on the field trip, the texture and tenderness of steak, depending on how well done it is. How heat transfer works when you are baking a cake. The temperature at which we cook cake is defined in such a way that it's going to have the best effect and not burn parts of the cake, but also cook it in a timely manner. Um, all the other examples were cooking, but freezing is also an example of heat transfer. And so understanding freezing processes and what happens to the food products as you freeze them is also really important in food science. So two main forms of energy are potential and kinetic energy. So all energy can be classified into potential or kinetic. And so potential energy is energy that is stored. It can also sometimes be called the energy of position. So in this example here with the guy on the bike, he has high potential energy because of his position on the hill. It can also be considered a measure of work done. So again, using this example of the guy on the bike, he's at the top of the hill because he's done all of this work to get there and has built up this potential energy that then can be used later. Kinetic energy is the energy of motion. Now, it's not always what we think of as motion. That motion can be at a beyond microscopic level, but things are generally always moving with kinetic energy. So I wanted to show you something with this simulator that if you are in my chemistry class last year, you've seen me use the simulator quite a bit, but not this particular simulation. This website is from University of Colorado or Colorado University, and they have lots of simulations for chemistry, physics, biology. It's called PhET. It used to be just about physics, and now it's just and so the FPH stood for physics, but now it just stands for nothing because they encompass so many different scientific fields now. So we're going to go to this one that is a skate park, and let me pull it up. It's not pulling up. Hold on. Not showing. There it is. Okay. Okay, so here's the skate park, and it's going to show you what I want you to pay attention to is this graph on the left that is showing the kinetic and potential energy. So you can change the little figure that I made this one a cat. Okay, and so at the top of this ramp, this cat has high potential energy because it can go super fast down this ramp. The lower I put it on the ramp, the less potential energy it has because the less momentum it's going to be able to get going down the ramp. If I have it at the bottom of the ramp, there's pretty much none, right? Or if at the very bottom, there's none. Okay, so I put him on the ramp, set him off, and you can see as he goes down the ramp, the potential energy drops. But the kinetic energy is increasing all the way up until he gets to the fastest point that he's going to be at the bottom, and then it decreases. Once it gets to the bottom, you'll see it goes up and it decreases until it gets to the top again. And so I wouldn't say that they are necessarily like a completely inverse relationship, but there is some inverseness to the relationship between potential and kinetic energy. Because potential energy is energy that is being stored up, and once it starts being used and used for motion, then it's being transferred into kinetic energy. Okay, and I want to see something funny. If I decrease the gravity while he's already got some momentum, he just kind of, well, he's not going to do it now. I did it at the wrong spot. If I decrease the gravity while he's got some momentum going on, woo, he goes off into space. Okay. So the book also breaks down the kinetic and potential energy into external and internal energy. So you can have external kinetic, external potential, internal potential energy. And it defines it as external energy is energy applied to an object by another source. Essentially, it's like you can see that thing moving, okay? Whereas internal energy is the energy within the object. And so the way that I think that's best described is, okay, this person is sleeping, but there are lots of internal processes that are still going on. There is blood movement. There is our chemical reactions where during a chemical reaction, those atoms are actually moving and going into place during those chemical reactions. And so those would be internal energy. And so generally that internal energy is the result of forces between atoms and molecules within a system. Now, these are not really well used terms, external, internal energy beyond this book. So I don't think they're super important, but the book does break that down. So both external energy and internal energy can be potential or kinetic. So if external is easy, right? But internal, so potential energy for internal would be, for example, you are storing glucose or fat in your body as a form of energy for your body to use later. When your body decides to use it for energy and takes it from the location it's being stored and has chemical reactions, then it becomes kinetic. All right, so it's potential while it's being stored and kinetic once it's being used. Okay, so on page 119, there is this figure on the top of the page. And you can see my nice big X because we are not going to use this. I don't like the way that they have this broken down. I think a lot of it is pretty incorrect. And so what we're going to do instead is use energy descriptors from the U.S. Energy Information Administration instead. So there are more for you to learn, but I think it will be more simplistic and really just make more sense. Okay. So that being said, you can skip all of the main text in the book from page 119 to where to the end of nuclear energy on page 125. Yep. So all the way up until it says measuring energy, and that's where you will start up again. That said, in between all that, there is extra material, in those little extra boxes. So it says like science matters and technology matters and microwave safety, healthful food features. Okay, so all that stuff you are still going to read. Okay, so still read the extra material in those little extra boxes, but the main text I want you to skip and only rely on what I am covering in this lecture for that part of the material where we're going over the forms of energy. Okay, so what we're going to do here is we have energy. We've broken it down into potential and kinetic. And within those, there are different types of energy. So potential energy, we have mechanical, chemical, nuclear, gravitational energy. And then kinetic, we have motion, electrical, radiant, thermal, and sound. Okay. Okay. So mechanical energy as potential energy is the energy stored in objects by tension. Now, I will note on mechanical energy that, so in the book, it does have it as both potential and kinetic, and you could still do that. And you'll see when we go over the motion energy, often that is what is called mechanical energy on the kinetic side. Okay, so the motion energy could also be called mechanical energy, but for this, because we're following what the government website says, we're going to call this mechanical energy and the other one motion energy. But for this, it's energy stored in objects by tension. So you have the Angry Birds example with the slingshot, someone pulling back a bow and arrow, you holding your arm back, and there is some tension to throw that ball by the baseball player. Those are all potential forms of mechanical energy. They have not released that bird or arrow or ball yet, but there is potential there with energy being stored. Okay, chemical energy is the energy that is stored in the bonds of atoms and molecules. So some molecules, when we break that bond, it's going to release that energy into another form. And then of course, when we make bonds, usually we're going to be now storing more energy because there's a new bond there. So the breaking and formation of bonds, this is another place where the book is wrong. So if you are reading the book, you're going to be off here. The breaking and formation of bonds does not just form chemical energy. It can form thermal energy. So what I want you to understand is that really it's storing the energy in the bonds when we are referring to chemical energy. Okay. Now, chemical energy is how energy in our body is stored. It is our fuel source for energy. So like I was talking about earlier, fat, glucose, ATP. Okay. All of those are energy storage for our body, and it's stored in the form of chemical energy. Okay. Nuclear energy is energy stored in the nucleus of an atom. It's the energy that holds the nucleus together. And I'm not going to go much beyond that. We'll get a little bit more into nuclear energy in a little bit. For gravitational energy, this is one that is not in the book. It is energy that is stored in an object's height. So the higher and the heavier an object is, so think about at the top of a roller coaster, the more gravitational energy is stored. Thinking about the simulation I showed you when that cat was close to the bottom of that ramp versus up high, then there was less potential energy, right? And that is gravitational energy. When he was high up at the top of that ramp, had a high potential energy because it was high gravitational energy further to go down. And when he's lower, then there was less. If I had switched from the cat to a human and changed the weight, you would also see that the potential energy would increase at the same height because of that weight. Okay, so now moving into kinetic energy. The first one we'll do is motion energy. And so like I said, this is sometimes also called mechanical energy, but the US government website just distinguishes the two. So motion energy is simply energy that is in objects that are moving. So the faster that object, the more energy. Remember, this is kinetic, so we are actually measuring kind of speed of movement there. Electrical energy is energy produced by the movement of electrons. Okay, so again, kinetic, there is movement. And what is moving is the electrons. And electrons are transported through anything that's a good conductor of electrons. Now, it doesn't have to be metal, but metals like copper and silver are what we think of mostly in our wires, and great conductors, but of course through the air, right? Lightning traveling through the air can happen too. Okay. In the book, they have electrical as a potential energy as well. I would most definitely argue with that and say that potential energy that goes towards electrical energy when it becomes kinetic is not stored as electrical energy. It's stored as chemical energy. Radiant energy is energy transmitted in the form of electromagnetic waves through some space or medium. So the key thing here is that it's electromagnetic waves. You're going to see another waves in a minute. That's not electromagnetic, and it's a different kind of energy. So the higher the frequency in radiant energy, the greater the energy. Now, what I mean by frequency, let's just say that these lines represent time. They're actually just separating out the types of energy, but let's say they represent time. Okay. So in radio waves, there are much fewer waves per second that are occurring across the space. Okay. Versus gamma rays, there are a lot more. So this is a higher frequency. You get more waves for the same amount of time. And this is low frequency. The higher the frequency, the greater the energy. And if you think about what damage some of this stuff can cause to your body, so gamma rays is like it's used in medicine, but it's radioactivity, right? And so this can cause some serious damage to your body if you're not careful. Versus radio waves are pretty harmless, okay? And that's because there is a lot more energy in these high frequency waves. Thermal energy has to do with heat. So heat is the energy that comes from the movement of atoms and molecules in a substance. And the faster that movement, the greater the thermal energy. Okay. Oh, this is not going to work the way I thought. I was hoping that I would be showing you a video, but it's not going to work. Okay, let me pause this and we're gonna get a video up. Okay, so I'm going to show you a different simulation that is the goal of this simulation is to show states of matter, which we're not really covering right now, but what I do want to show you is what is happening as we increase temperature with molecules. So I'm going to switch this to oxygen, and so right now it is at negative 246 degrees Celsius, super duper cold. Okay, not a whole lot of movement among those molecules. You can see once I start increasing the temperature, they start wiggling around quite a bit more. Okay, so now so it transitioned from a solid to a liquid, I would say. This is liquid oxygen, still super very, very cold, so it's still liquid. But oxygen doesn't have to be too warm to become gas. And so that movement increases until they're actually flying all over the place. Okay. So with a solid, just very tight vibrations, and the movement becomes more at temperature. But even within a phase, so we are definitely in the gaseous phase, right? When I increase the temperature, that movement increases. Hopefully you can see that there's a lot more movement going on than there was when it was colder. And we're still like below zero, so it's slow. Okay. So there is more thermal energy going on here, contained here, than there was a minute ago when the temperature was lower. Okay, so this is about body temperature. Body temperature is about 35. Okay. So faster the movement, the greater the thermal energy. And that movement comes from heat. Okay, sound energy is the last one that we'll talk about, which is not in the book. But sound energy is a thing. It's energy that is moving through substances. It's also in waves, but these are not electromagnetic waves. Okay, so these sound energy waves are produced when a force causes an object or substance to vibrate. So it's vibration. And energy is transferred through that substance in a wave. The key thing is it has to go through a substance. So sound energy is the least amount of energy of all of the types of energy. And just kind of a more trivia note. So they say sound does not travel in space because in space there is nothing for the sound to travel through. Space is a vacuum. And so there is no gas like there is on Earth for the sound to travel through. On Earth, it's going to travel through oxygen, nitrogen, carbon dioxide, etc. gases in the air. For space, they don't have that. And so, the astronaut could be across from his rocket ship that just got hit by a asteroid and can't hear it because there's nothing for that sound to travel through. Now this astronaut, because he's attached to the rocket ship, could hear it because the sound can travel through his little attachment there. So, okay, now all of that by itself is not that helpful to food science. What is important, what was more important, is the fact that energy can be converted from one form to another. And that is where we get kind of the magic of, life, of food science, of life, of everything. Okay. So first talk about chemical energy. Okay. So when those bonds are made or broken, energy is stored or released. And so if it's stored in the form of chemical energy. But if it's released, often it's going to be released in the form of heat. So when that bond is broken, that chemical energy is converted to thermal energy. And when that happens, it is going to be an exothermic reaction. And the term exothermic comes from exo, which means outside, and thermic means heat. So you have outside heat, and essentially energy is being released during the reaction, and it's released in the form of heat, so you feel warmth coming from that reaction. The opposite of that would be endothermic reactions, where thermal energy is converted to chemical energy. And so endothermic comes from endo, which means inside, and thermic still means heat. And in this case, the energy is going to be stored during the reaction as chemical energy. Okay, so either way, there's a conversion going on of different types of energy, but it's just whether it's a net release of energy or net storage of energy that's going on. Now, I mentioned a little bit earlier that electrical is not a potential form of energy. It's only kinetic. And when we are getting electrical energy from something, it's coming from some other potential energy, which is often going to be chemical. Now, I am not an electricity person, though it's possible I'm getting this a little bit wrong. I'll admit that. But let's just think about the term in battery terms, okay? So like I don't know how electricity is stored like at a power plant or anything. But in battery terms, batteries store chemical energy. We have chemicals that are in different parts of the battery, and then the electrons travel once this battery is connected from one side to the other, and you're producing electricity. Okay. But initially it's just as chemical energy, potential energy there. Nuclear energy. So nuclear energy is a potential form of energy, but then we can use it and convert it to other kinds. Okay, so it can most definitely produce thermal energy, such as in the atomic bomb, but it can also produce electrical energy, such as a nuclear power plant. It can also produce radiant energy in the form of like electromagnetic waves, and that can be used in the food science field. So this here example is strawberries. On the left side, these strawberries have been irradiated, and on the right side, they have not. In the irradiated strawberries, irradiation was produced potentially from nuclear energy, and it killed all of the microorganisms that were on the strawberries, such as the mold that you see here on the right, and left those strawberries staying fresh for far longer. than a regular strawberry, which there's mold in the air. There's mold where the strawberries are grown, and so that's just naturally a part of it. And then they get packaged, and they succumb to mold. And so irradiation can produce that just by preventing overgrowth of microorganisms. Now, not all food irradiation comes from nuclear energy. That's just one form. And in fact, probably most doesn't. Also used is electron beam irradiation, which is produced through electric current, and X-rays, which are produced by accelerating electrons through a voltage drop. So it's also kind of electron or electrics that produces X-rays. But nuclear is one conversion that can be made to get the radiant energy used for food irradiation. Okay, so electrical to motion. So just examples: drone, battery. So then you have chemical to electrical to motion, to motion, right? Or food science example is a mixer, right? Plug the mixer in and we get that motor running and motion. Okay, electrical to thermal. So that's an easy one, right? Plug in your oven or your air fryer or your toaster and you get heat, and that's cooking our products. Microwave ovens. Those are going to convert electrical energy into microwaves, which are a form of radiant energy. So the microwaves are then absorbed by the water, the fats, the sugar, other molecules that are in the food. And once they're absorbed, they vibrate, and that vibration produces heat, which is thermal energy. And the heat ultimately cooks the food. So you have three things going on there. You have electrical to radiant to thermal to cook the food with a microwave. Okay. Another cooking example is the energy conversion from electromagnetic waves. So obviously this induction cooktop is plugged in. So you have electrical, and then electromagnetic waves are produced by that unit, which create a magnetic field, excites the electrons, produces a low electric current in the pan, and causes the pan to heat up. So lots of energy conversion going on there. You have electrical to radiant to electric to radiant to thermal. And I mean, it's just kind of great that all of that conversion leads to something that if you never use an induction cooktop, you can turn it off and immediately touch the cooktop, because there's no heat stored in the cooktop, unlike like your glass, your flat top stove or anything like that. Okay, so what is heat? Just want to define that a little bit better. So heat is the energy transfer from one body to another caused by a temperature difference between the two bodies. It's slightly different from thermal energy. Okay. It always flows from hot to cold. Okay, so heat always goes to the spot with less energy, not vice versa. Cold does not make something hot less hot, and it's the opposite. Now, when that heat goes to the cold, it loses some of the heat, but the actual mechanism is that the heat always goes towards the cold. Okay, heat is measured in calories or joules. In the US, we pretty much use calories, but in the scientific field, we'll use joules a lot. In chemistry, we use joules. Okay, so a calorie is the heat required to raise the temperature of 1 gram of water 1 degree Celsius. And I do want to make the distinction, if you haven't had chemistry yet, the difference between capital C calories versus lowercase c calories. So what you know, just as a general consumer, is the capital C calories. So a calorie, like we see in nutrition facts with a capital C, is not the same as the calorie that we are using here, which I have a capital C just because it's the beginning of the sentence here. But it's a lowercase c calorie. So this is not the same. The heat required to raise the temperature of 1 gram of water 1 degree Celsius. Okay. The capital C calories that we have on nutrition facts is actually a kilocalorie or kilocalorie. Which is the same as 1,000 calories. And the reason for that is, like, people just didn't see the point in, number one, they were going to round anyways. But number two, do we really want to have on our nutrition label, this has 220,000 calories? And it's just much simpler to just say 220 because we're not going to be measuring it down to the nearest single calorie anyways. That would not be... the precision is not there in the food. So it wouldn't make any sense. And so instead, we said if we say have a capital C calorie, then it is 1,000 calories, and that is what goes on our food labels. Okay. Heat capacity. Okay. So I don't really like the book definitions of heat capacity and specific heat, so we're going to change the definitions that you should know. So instead of the ability of substance to absorb heat for heat capacity, we're going to use heat capacity is the amount of heat required to raise the temperature of an object 1 degree Celsius. Okay. Keyword here that is going to distinguish this between specific heat capacity is object. Okay, you'll see in a second. Okay, specific heat, which could also be called specific heat capacity. So the book is referring it to it as specific heat, but in some places you'll see it as specific heat capacity. Same thing. Okay. And having that capacity there helps you actually understand a little bit more what the difference is between heat capacity and specific heat capacity. So the book says something about compared to water's ability. Ignore that. Instead, we're going to use the amount of heat, thermal energy, required to raise the temperature and notice that so far all is word for word the same as heat capacity until I get to here, of 1 gram of a substance by 1 degree Celsius. So instead of an object, which is what heat capacity was referring to, now I'm saying specific heat capacity, that it's 1 gram of a named substance. Okay, by 1 degree Celsius. So, so also the book says something about heat capacity of water being high. So it is the specific heat capacity of water that is very high, not the heat capacity of water, because water as an object, like it depends on how big it is or how much water you have there. So specific heat of the water is very high. And so what that means is if you have to put a lot of heat into a substance before the temperature goes up by 1 degree, because that's what a high specific heat would mean, is that we have to put a lot of heat into that to raise it by 1 degree. That means that the water absorbs the energy without the temperature going up. Okay. And so it requires more heat to get pure water to a specified temperature than most other substances. Okay. And so what that means practically is that foods with a high water content take a longer time to cook. Because the more water is in there, then the more heat is going to have to go into that to get it to increase in temperature. Okay. So, in relative terms, specific heat. You just use some common terms here. Okay. Specific heat is how difficult it is to change something temperature. Okay. So a higher number of specific heat capacity means that it's going to be more difficult to increase or decrease that substance's temperature. Okay. The higher specific heat means the substance absorbs more energy without increasing in temperature, and vice versa. So if we're trying to lower the temperature, it's going to release more energy without decreasing in temperature. Okay. So again, practically, actually, let's think about foods. So here are some specific heats of some different substances. So we have water, which is the highest, 4.19 joules per gram per degree Celsius. Olive oil is about half that. Okay. So oil takes about half the energy to increase in temperature the same amount. Milk, very close to water. Okay. If ground beef, 3.52, potato, 3.43. Now, most of our food items are going to be, as far as specific heat, somewhere between olive oil and water. Oil and water, okay? Because that is what a lot of our foods are made of. They have a lot of oils and waters in them. As far as things that affect the specific heat, but things that we're cooking, okay? And so that's important. So practically speaking, it takes more energy to increase the temperature of water than oil. But once the temperature is high, it's going to stay high for longer and be transferring that heat energy to the foods it is surrounding better compared to oil. So like you turn off the heat, if I take this boiling pot off the stove, it's going to stay hot for twice as long as the same pot of oil taken off at the same temperature. Okay, we generally heat oil a little bit higher than water, but let's just say they're the same temperature. And thus, it will continue to cook the food that is inside the pot for longer. Okay. Thinking about foods, then the higher the water content is in a food, the more energy it's going to take to heat that food through. And also, because it has water in it, it will continue cooking once it's taken off the heat versus something that is more oil-based. Okay. So temperature. So temperature is different than heat. Temperature is the measure of the average kinetic energy of a group of individual molecules. Okay. It is an indirect measure of thermal energy. Okay. So the difference here between temperature and heat. So heat is the transferred to an object. So for example, how the stove heats the pot. But temperature is just how hot or cold that object is. Okay. So temperature, it only measures that molecular motion in the space that it is in. And so it's not the same as heat, which is an energy. Okay, last slide here is thermometers. And just kind of to point out that one thermometer is absolutely not the same as another, and you need to choose your thermometers based on the function. Okay, so This first thermometer is a Thermopin. It's probably the most useful thermometer in this whole set that I'm going to show you. But this particular thermometer has a very broad range, and it is very, very accurate. And so, yeah, it's probably the best one here. I have one. Yeah, so Thermopin. Okay, notice they were kind of initially made for meat functions, and so that this probe here is a sharp probe that's made for going into meat, but it'll puncture most foods too. Okay, so this next one is a meat thermometer, but it's one that is made to stay in the oven. So a Thermopin, it's not meant to stay in the oven. Thermopin is called an instant read thermometer. So you stick it in, and within 30 seconds, generally less, within 10 seconds, you have the reading. Okay, a meat thermometer is, or an in-oven meat thermometer. This is not going to be instant read. Okay, you're going to slowly see this dial go to where it is, and then it'll stay steady for once it's finally gotten there. But this is actually meant to stay in the oven, so you can just put it in your meat item and just open the oven and check on it whenever and see where you're at with temperature. Okay. The next one is an oven thermometer. So notice the difference in the range here. So this meat thermometer, it starts at 120, where this is Fahrenheit, and goes to 220 is the max. And because we don't expect that meat to get above 220, all right? The meat, it doesn't get that high. There's a limit to it. Versus the oven thermometer is starting at 100 and can go all the way to 600 because we can get those ovens pretty hot, right? And so the range is something that you need to consider when selecting your thermometer. Also, because not all thermometers are going to have the range you need for what you are working with. Okay, so speaking of that, this is a candy thermometer. Okay, so the candy thermometer, when we are heating sugars for candy, that temperature goes up way high. Sugar boils at a much higher temperature than does water. And so you can get it to a much higher temperature than meat also, for example. It's hard for me to tell where this thermometer ends up. I think it's around 400 is the max temperature on there. So 400 degrees, that's significantly higher than what this in-oven meat thermometer can achieve, right? But we need to be able to read it that high because with candy, different temperatures result in different types of candy. So you have, and I am not a candy expert with food science, so I will be by the time we teach that part of the lesson or part of the class. But at a lower temperature, you have more of like a taffy type candy, and the higher you heat that sugar, the harder that candy becomes. So the hardest candy is actually heated super high temperatures to achieve that hard candy, and it'll be liquid. You pour it, and then it'll solidify, and it'll become hard candy. And the difference in what that texture of the candy is going to be can vary drastically within just a couple degrees. And so not only do candy thermometers need to be to read high temperatures, but they also need to be very accurate. Okay, this next one is a freezer or fridge thermometer. So you definitely would not want to use this for cooking because number one, precision, accuracy is not going to be great. But number two, if you look at the temperatures here, it's only going up to 80 degrees Fahrenheit. Okay, but it goes down to -40, right? But it's not going to be useful for cooking at all because we're going to cook anything above 80 degrees Fahrenheit, right? Okay, this next one is I'm just going to call it a barbecue thermometer. And it actually has 4 different probes on it that all plug in, and you can read the temperature of 4 different things at the same time. So one of them, you might be reading the temperature of your grill itself. So this works real nice for people who are doing overnight barbecue, cooking the briskets. And so you plug in one of the probes and you just have it sitting in your grill, and then other probes you can have in your meat product and monitoring the temperature of that over time. This one is actually wireless, so it sends the temperature readings to your phone or to a wireless device that's included with it. Some of these, you can actually connect them to fans, and it will, like you can have a fan plugged into your grill, and if the temperature gets too low, the fan will start sending air through there because air increases the fire and increases the heat. And so it'll actually not only monitor the temperature for you, but regulate it for you too, which is pretty cool. So then we have a body temperature thermometer, right? That's not going to be useful for cooking at all because once it gets above, like 107 or so, it's going to just give you an error and say, nope, there's something wrong. This is not what I meant to measure. Okay. We have a wall thermometer, which also is going to give you trouble past 120 degrees, which is well under what we're cooking anything to. And how you're going to, you're not going to be able to get that into an oven without it melting, and you're not going to be able to probe any kind of food with that either. Okay, and then this last one we'll actually use in our class for different things, but this is just a lab thermometer made out of glass, and we really probably don't want glass thermometers going in a lot of our food. There is glass here, but not being inserted into the food. So yeah. So purpose dictates which thermometer you're going to use in any of your cooking applications or kitchen applications. All right, so that is all we have for this first section of Chapter 5. Make sure that you are noting the things that are different from the book, because this is more than just extra credit for this lecture. This is important stuff that I am telling you, nope, this is changed, and everything on the exam relating to the things that I have mentioned are changed, is what I expect to see from you. So have a great week.